This last example, I'm not going to lie, this is probably the thinkiest example here in this section. We're going to extend the conversation with numbers, finding the sum of the numbers from 1 to n, or those triangular numbers. And we're going to extend that to pentagonal numbers. These are numbers that form a pentagon, five-sided figure. And I have the first 4 of them represented here. We're going to find a pattern on finding the number of dots in the nth pentagonal numbers. This is going to use a lot of algebra, and it's going to use a very similar thought process to those examples we did with the triangular numbers in the sum from 1 to n. So in our first pentagonal number, there's just 1 dot. Easy enough. So in our first one, we just have 1 dot. In our second pentagonal number, and you can notice I've got a color difference. So in our second one, we have 1 plus 4, or 5 dots. Okay, so 1 plus 4. Moving to our third pentagonal number, I have 1 plus 4, and then when we add out here, we're going to get plus 7. So when we add 1 plus 4 plus 7, we get a total of 12. Our fourth one, we have 1 plus 4 plus 7. And again, we need to add out here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 plus 4 plus 7 plus 10, add those together and we get 22. Now, can we see a pattern? Hopefully you can here. When we're going from one pentagonal number to the next, sorry about that, we're adding numbers that are 3 higher than the one before. So 1, then 1 plus 3 is 4. 4 plus 3, 7. 7 plus 3, 10. So we're doing our 5th pentagonal number. We're going to have 1 plus 4 plus 7 plus 10 plus 13. Okay. So we'll end up with 35 as our total. So hopefully you can see that pattern. But what if we're asked for the number of dots in the 70th pentagonal number? It would be a lot of work to just continue writing out this pattern until you get to 70. So we're going to look for a formula. So I'm going to base it off of the 5th one here. Let me switch to a different color. So follow what I'm going to do here. So there's 35 total. And I'm going to rewrite these numbers a little bit. 1, I'm going to write as 1 plus 3 times 0. 4, I'm going to write as 1 plus 3 times 1. 7, 1 plus 3 times 2. 10, 1 plus 3 times 3. And then 13, 1 plus 3 times 4. Now, I want to look at the nth pentagonal number, and I want to find the sum of the nth pentagonal number. I'm going to use this idea here, but we're just going to extend it, okay? So for the nth pentagonal number, let me rewrite this. I'm going to let P sub n represent the sum. So following this pattern, okay, we would have 1 plus 3 times 0 plus 1 plus 3 times 1 plus 1 plus 3 times 2. And we would take this all the way up to 1 plus 3 times n minus 1. Now, why am I stopping here at n minus 1? That's where my previous pattern stopped. So the 35 is our fifth pentagonal number. It went up to 1 plus 3 times 4, so 1 less. So that's why this is n minus 1 here. Now, we're going to do this very similar to how I did the other ones. So what I'm going to do is I'm going to rewrite this, but I'm going to put it in the opposite order. So you could also write this as 1 plus 3 times n minus 1 plus 1 plus 3 times n minus 2, working our way backwards, plus 1 plus 3 times n minus 3, all the way down to 1. So starting at the largest and working our way down. So then I'm going to add these together. So this one is going to take a little bit more work. When we add these together, what do we get? So 2 times p sub n, that's the easy part. Now let's add these different pairs together, okay? So let me start with this first pair right here. 1 plus 3 times 0, well, that's just a 1. Then down here, I have another 1 plus 3, I'm going to distribute 3n minus 3. So when I combine like terms, all of this ends up equaling 3n minus 1, right? 1 plus 1 minus 3, 2 minus 3 is negative 1. So I get 3n minus 1. Now I'm going to look at my next pair. Here we go. 1 plus 3 times 1 is going to be 4. So 1 plus 3, that's 4. Plus 1, and then distribute, plus 3n minus 6. 4 and 1 is 5. 3n minus 6. 5 minus 6, I get another 3n minus 1. And it turns out each pair that we add is going to equal 3n minus 1. So I have n of these 3n minus 1s. So I can represent this sum, 2 times p sub n is equal to n times 3n minus 1. So the sum there, the number of dots, is equal to n times 3n minus 1 over 2. So now we have a generalized formula for the number of dots in a pentagonal number.